People are starting to come in, Gordon, so I'll just, we're not going to do introductions this time, but everyone, we are here for the fifth session of our nutrient amendment summer series. And today we're with Gordon Price again, and we're talking about conversions of feedstocks into soil amendments. It's nice to have the title right there. And this session is being recorded. We'll do the questions at the end of the presentation, if that works for you, Gordon. And I think that's everything. This will be on the OFCAP website probably within a month or so. So stay tuned for that. And Gordon, you can take it away.
Great. Thank you, Georgia. Welcome, everybody. Today is my third webinar in the series, and today I'll be speaking on the conversion of feedstocks into soil amendments and also identify a few sort of different and potentially novel approaches to generating soil amendments. As I mentioned, this is the third, so I've covered an introduction to soil amendments and management considerations for soil amendments. Today, we'll be looking at some conversion processes and novel soil amendments, as well as some of the considerations around those conversion processes. And the last webinar in the series, for me at least, will be related to understanding biosolids as soil amendments. And I believe the date is going to be August 6th, so the question mark will be removed shortly. So when we talk about soil amendments and conversion processes, as I've discussed before, there are a number of considerations around how we might want to use raw soil amendments. We might even consider them as raw feedstocks towards the process of generating new soil amendment products. And in this particular graphic here, you can see that there's an anaerobic digestate, compost, vermicompost, biofertilizers, and biochar or engineered biochar. And these illustrate some of the different approaches, technologies, techniques, processes that can be undertaken to generate different types of products from, essentially the same feedstock sources. And the reason we do that, is possibly for, often it is for improving soil fertility. There are cases where the final product, such as biochar, may serve a purpose for soil remediation because of their high surface reactivity and capacity to immobilize contaminants such as heavy metals. Likewise, there may be improvements based on what the material is allowing the microbiology to release that may offset pathogenic organisms, reduce the incidences of plant disease, or potentially increase nutrient use efficiency or increase or improve nutrient cycling. So some of the processes to generate soil amendments, before we get into them specifically in terms of the processes, I just want to go over a little bit of terminology, terms that you'll hear today. So compost is generally meant to indicate materials that have undergone some type of microbial conversion under what we would call managed conditions to result in a biologically stable product. Vermicompost is not quite the same as a compost itself, but the vermi component identifies that the worms or earthworms are involved, and so it's a range of materials that undergo decomposition that's aided through the interaction of earthworms and microorganisms. I mentioned my biofertilizers in my two previous talks, and I've modified the definition a little bit here as materials that are converted through microbial or other biological processes to generate products that will improve activity, reactivity, and nutrient cycling. Anaerobic digestion relates to materials that are decomposed in a reactor or some type of vessel or condition where there's an absence of oxygen. And biochar are materials that undergo a thermal chemical conversion under low to no oxygen to generate products that often have high surface reactivity, and depending on the temperature and the retention time within that thermochemical system, possibly more chemical stability. So some of the considerations I've talked about before around the use of soil amendments, will relate to your purpose, the need that you may have. It may be the fact that your farm, your location is generating a large volume or large quantity of these materials as raw feedstocks, and you're looking at a process or a mechanism to recycle that material or to dispose of it in a way that is easier to transport or more easier to handle. There may be instances where off-farm materials are brought in order to generate a specific product, mixed in possibly with materials that are being generated on-farm, biomass generated on-farm, that you want to convert it into a product that you have a specific use for. And some of the other considerations, obviously, both for the raw feedstock and for the final products, will then relate to the chemical and physical and biological constitution, composition of those materials. Likewise, when we're talking about the generation or the processes under consideration for generating a soil amendment, the requirements of processing, so that could be equipment, electrical or energy requirements, are an important consideration, as well as the potential benefits. And so we're not looking at materials that necessarily are going to be giving you as the user, as the generator, a single benefit. For instance, you're not necessarily looking at just fertilizer value, but hopefully you are layering several tiers of value and opportunities from that material. And I'll discuss that a little bit in the context of some of the examples I'll present. So I've illustrated these different materials before to talk a little bit around the the different shapes, fineness, the coarseness, uh, the the nature of the materials themselves, whether they're highly liquid or more fine. And these general considerations for converting raw feedstocks into amendments are become a very important component of your pathway towards a product. So we start with quantity and access. So here in this particular graphic or set of graphics, I'm just going to sort of talk about the capacity that we have globally, both from our land production for food and feed, as well as just the land that's available and producing biomass. It's estimated to be somewhere around 50 billion tons. And of that 50 billion tons, we are producing biomass typically for a range of purposes, such as grazing, feed, for animals, food, energy crops, woody materials. And of that biomass that's produced globally, we have about half the amount that's generated as a byproduct from those processes and are potentially a harvestable biomass for use, again, as a source of fertility, as a source of carbon sequestration. And in many cases, these are materials that are not actually being utilized most efficiently. So quantity and access become an important consideration for where you're located, or for the type of technology or approach that you may be considering. So with respect to the raw feedstocks, we go back to the chemistry of that feedstock in terms of its nutrient content, its fertility value, its carbon content. Very important criterion for the raw feedstock when we're trying to evaluate the best process to undertake is its water content, and this could be in the raw feedstock stage and becomes certainly critical piece when we're thinking about how far you need to transport this material, both as a raw feedstock and likewise at the end when you have your product. How far are your materials going to have to transport, and how much water are you transporting relative to the inherent value in the material. Physical form will help determine how much pre-processing and the type of equipment that you may need, so how coarse, how fine the material is. And finally, each process may have different capital or infrastructure requirements for different scales of generation of your soil amendment from the different processes that we'll be discussing today. So I'm going to start with composting and compost. Composting and compost is essentially a process where we are attempting to mimic nature. It's a controlled biological process under oxygen conditions or aerobic conditions where we're decomposing organic materials, and we are actively managing the conditions such as the temperature, the moisture content of the feedstocks, pH, carbon, nitrogen content of the mixtures, oxygen, so that the microorganisms that are involved in that organic matter breakdown are able to survive and are able to actively participate in the breakdown of the organic matter in towards a final material, which will be a compost that will be biologically stable and provide us a number of benefits. I mean, these benefits could include that where the stabilization of that organic matter, which reduces both volume, but also improves our handling of that material, as well as depending on the nature of the process that you take in it. If you take it through what we term a thermophilic process, then pathogens, weed seeds may be reduced in their capacity to carry over when the material is used in soil again, or may ultimately be destroyed. And you know, the final product, of course, as a compost is some sort of value as a soil amendment. The value could be as a carbon source, as a structural material for improving soil physical properties, and in addition to that, providing a range of benefits associated with fertility for plant production. So the process of composting in insofar as we are trying to control the various conditions around decomposition, is taking the raw materials through some process. It could be a mechanical process, it could be a manual process towards a final material that is humus looking and stable. And through that process, we're going to be managing the way that temperature or heat is released. So we'll be managing the temperature of the pile. Carbon will be released, so we need to be managing the ratio of carbon and nitrogen. Moisture content's important as a mechanism to allow microorganisms to have sufficient moisture. However, we need to manage moisture in the same context as we would with any other living organism. Too much moisture can lead to conditions changing from aerobic to anaerobic, and insofar as that change occurs, then we are changing the chemical reactions that are undergoing in that process. So particle size and surface area, as well as pH, may be other determinants of how effective this process is. So we're trying to mitigate odor. We're trying to control odor. Water and heat will be released. And through this composting process, you as the manager of that process will have to make decisions and determine when to mix your pile, when or how to add air and oxygen into that pile, how you're going to manage your carbon to nitrogen ratio. Typically, that's done at the very beginning when you're making your mixtures, but in some cases, you may not have the luxury of being able to generate a clear recipe, and so you may be bringing in external feedstocks to moderate the material's carbon to nitrogen ratio in order to achieve the more optimum reactions. I've presented tables like these. These are available in a number of different documents in literature that's available either through the internet, through purchase through different conservation services. And just as a reminder that the microbial carbon to nitrogen ratio typically ranges from 8 to 10. So when we're looking at your specific materials, materials that have a C to N ratio that's closest to that microbial C to N ratio are very likely to decompose very, very quickly, and that may not be a good thing. So that may be a strong consideration with respect to if you're working, say, with a broiler litter that has slightly higher nitrogen but has a fairly low carbon to nitrogen ratio, that it may mean that you have to bring in another material, an external material that will help offset that lower C to N ratio and bring it up to a level that will slow down the decomposition rate so that you're not releasing materials too quickly and potentially losing the optimum conditions. Again, you can see here that there are all sorts of materials, fruit waste, culled potatoes, potato processing sludge, soybean meal, vegetable produce, and waste that all have quite a range of different characteristics, both from their density to their moisture content to their C to N ratio. So that recipe development can take on a number of different forms if you have the opportunity to access different quantities and different types of material from around your particular location. When we're talking about optimal composting conditions and the things that we're trying to manage, we're really trying to manage an overall moisture content of the mixture of your different raw feedstocks. So typically we're aiming for a mixture of 50 to 55% moisture content or water content. And this can vary depending on where you are. If you're in a location that's quite rainy, there's a lot of rainfall, and your compost piles are going to be outdoors. Then you may aim for a slightly lower moisture content of your initial mixture if you're expecting a large amount of rain to occur and potentially enter into your compost pile. C-to-N ratios, you'll often find a recommended C-to-N ratio of 30 to 1. And as I was illustrating the table before, your materials may vary quite widely. And so they're your mixtures, the determination of the ratio of mixtures of different feedstocks will play a role towards determining how close you can get to that 30 to 1. It's not a perfect science. Different materials will decompose at different rates, and it'll depend much on the physical characteristics, such as the particle size, how coarse, or whether there's a waxy layer on those raw feedstocks. So really, this C to N ratio is a target and not an absolute. Certainly, some of the key aspects of managing a compost pile are trying to maintain that oxygen content. Microorganisms are going to consume, if they are consuming the food in that mixture quite rapidly, they will be consuming the oxygen in that pile quite rapidly. And so ensuring some mechanism of introducing air and mixing that pile through mixing the pile or through some other means can be quite an important management piece to consider, particularly at the early stages. If you look at the curve or the figure on the left-hand side of your screen, these offer two different perspectives on the optimum temperature profiles that we'd be looking for in a typical composting pile. The curve number one represents what we would normally see in a typical thermophilic pile. So this is a pile that we would consider to be very active, and in the microorganisms are decomposing material quite effectively. You notice in the number of days, the temperature peaks somewhere above 65, close to 70 degrees, peaks in less than 3 weeks. In some cases, you may see this peak within a few days, depending on the nature of your feedstocks. So this is a typical profile, although the number of days and the timing for those peaks may differ depending on your different recipes. Curve number two is a material that is not decomposing as effectively. It's decomposing much more slowly. It is peaking quite a bit later, and it's potentially not achieving the true optimum conditions that we're aiming for, particularly in the context of, say, pathogen management. And pathogen management, typically we'd be looking at temperatures over 50 to 55 degrees Celsius, or more effective pathogen management, and potentially the reduction of weed seeds. And so in this particular instance of curve two, we're not achieving that. And so there may be some issue with the management component, that maybe not enough sufficient mixing, or the C to N ratio may be slightly off, or the moisture content may be slightly off. So in the situation as curve number two, we'd be looking at troubleshooting that particular pile and trying to understand, what are the management steps that could be taken to offset that particular profile and improve it towards something that looks more like curve number one. An illustration of that from a real scenario. This is data from a study that we were involved in, and you can see here there are 3 separate windrows, and in all cases the windrows are achieving thermophilic conditions throughout 3 particular stages at day by about day 3, and by day 7 or so, about a week in, the temperatures start to drop. The material's mixed, and then you see another peak. That second peak in the thermophilic stage goes up to around 65 degrees. It's maintained for roughly 2 weeks before the temperatures start to drop again, and then we see another mixing event. The temperatures go up, and then by day 46, 47, there's another mixing event, and we don't see quite the same increase. And so at that point, we'd be considering these piles going into a curing phase, or a phase where the material is going to just be continuing to slowly decompose over a period of several months. So the optimum profile can look very similar to what I showed you before. However, the timing over how those particular phases are, or those peaks are achieved, may be quite different. This was a poultry mortality compost experiment, and so you can see that some of that material was, well, that material was very reactive. And so typically when we're looking at those two phases of thermophilic and mesophilic, we're really talking about 40 to 70 degrees Celsius for the thermophilic phases, and 10 to 40 degrees Celsius for that mesophilic. And then the mesophilic stage is around where most opportunistic organisms are active, whereas as you get to much higher temperatures, you got much more specialized organisms that are involved in that decomposition. Again, I've illustrated this a couple of times before, but it's a nice graphic to help you understand that once you have your stabilized, your biologically stabilized compost material, the reaction looking at here, the red line, the composted versus the fresh, when it's added into soil, is really reflective of the dynamic that we're trying to achieve. We're trying to achieve a much slower release of the fertility or the nutrients or the carbon in that material into the soil, so that there's less potential for loss of in any of those valuable resources early in the season, but that the value of that is, if we're considering, say, from a fertility perspective, the value of that that compost as a fertility source is being extended throughout the growing season, particularly in later stages of production, where the plant is starting to move into vegetative stages and is looking for higher amounts of nitrogen, phosphorus, and potassium. Again, so what we're changing with compost through that process of composting the material of raw feedstock is changing sort of the magnitude or quantity and the timing of nutrient release. An illustration from data. I presented this before, but I wanted to sort of highlight these two specific plant-based compost versus manure-based compost. Again, looking at that C to N ratio, the lower the C to N ratio, the faster and the larger the magnitude of release of certain components. So if you look at figure A, we see yard trimming composts, the low C to N ratio treatments, yard trimming, Zeolo Batch 5 and Solano. They have the lowest C to N ratio, and then they have the highest release of mineral nitrogen into the soil after application. Likewise, in the manure-based compost, low C to N ratios ranging from about 7 up to 12 to 13, and it's the low C to N ratio manure-based composts that are releasing the most amount of mineral nitrogen. You can see also the difference in the scale of these two graphs. The yard trimming compost upwards of 4% of the total N, whereas manure-based compost upwards of 30 to 40% of the total N of the material. So the composition of the feedstock matters. To some extent, what you are what you eat is that expression certainly plays a role when we're thinking about the use of different raw feedstocks and the processes that we want to use them in. So finally, for compost, I mean, key things to consider: aeration management, how we get oxygen and air into these piles. These are some much larger windrow piles. You can see on the right hand side with the PVC tubes. This is a passive a passive aeration technique. You would orient the tubes towards the general wind direction, the typical wind direction, to allow wind to pass through the pipes, and the pipes would have holes in them, and then the air would move its way up through the pile. Or you could have more mechanical active systems where you are pumping air through the piles. Typically, this is done in much larger, where you have much larger windrows or materials that you're trying to actively process. But moisture management also becomes a significant concern as well. So you have to think about the conditions that you're living in. Are you in a location where there's a lot of rain? And are you going to result in a large flooded puddle where all of those nutrients, all of those things that you're trying to maintain benefit from in the composting process may be lost through leaching? And so you may see in the right-hand side, the pile at the bottom, there a lot of the value of that compost material is going to be lost. It's going to be leached, or it's going to run over the surface, and in addition to that, may actually become a detriment as a pollutant in different say in different surface water bodies. So understanding the nature of your mixture, understanding the capacity that you have. So do you have a concrete pad or some type of an impermeable surface where you can do this type of work and maybe recapture some of that moisture, will be important considerations for managing a compost material, or managing a material as a compost. Two other slightly more novel, slightly different approaches to generating soil amendments, converting raw feedstocks into more stable, valuable products are vermicomposting. And so in vermicomposting, we're not trying to achieve the same optimum conditions as we would in a compost. We're not trying to achieve that thermophilic range at a very high temperature, because under those conditions, we're more likely to kill the worms than we are to effectively use the worms for what they're best at. So here we're using worms to essentially process the organic wastes in the best way that they are able to, which is to essentially act as bulldozers through a media. If you can think of an earthworm, if you're familiar with earthworms burrow their way through soil, they burrow their way through organic piles as a tube. Material goes in and material goes out, and the material that comes out is the product that we're looking for. You can see the worms in a compost in the picture on the right hand side, and then the buckets are buckets of the earthworm casts. And so the casts are essentially little micro pellets that the earthworms are releasing as they're burrowing their way through the media. And these casts are essentially little encapsulated pellets. They're micro pellets, as I mentioned, that are surrounded by a carbohydrate layer that's part of what the earthworms secrete in their gut. And so we have a rich carbohydrate layer that is gluing the media that is passing through the worm's gut and then being excreted and being held in that form. And so, we're essentially looking at a material that has been pre-processed for all intents and purposes by almost mechanically, but through this biological organism. And so when we look at the range of chemical parameters of these casts, we see that they have a ratio slightly above the microbial CDAN ratio between 12 and 15. Total nitrogen content between 1.5 to 2.5%, a phosphate content of 1.25 to 2.25, and potash of 1 to 2%. Moisture content tends to be a little bit high, but it can be dried down. So this is a material that has a range of value as a potential very targeted source of fertility, but it also may have some other biological features or microbiological features that are carried forward from the media through the earthworm that can be used as inoculants in whatever your growing production system is, whether it's ornamentals in a greenhouse or much larger scale field-based production. We had at one point through my research program looked at the potential of using very specific mixtures of feedstocks to generate a very more stable pellet type product, cast product for use on golf greens, because golf greens have very high specification requirements for the fertility, as well as high specification for low odor organic products. So we were attempting to use the earthworms to generate a product like that. We weren't able to get any golfing greens or golf courses to come on as pilot testers, but I think again, it's thinking a little bit outside of the box of the type of product that you may be looking to generate, and the characteristics of that product for non-traditional markets. And so again, how do earthworms do what they do? So here's an illustration. You can see at the bottom, in the bottom image, we have an earthworm in soil. They are tunnelers. They're gonna burrow through soil, and they're gonna create these tunnels. Those tunnels effectively create the aeration in a compost situation. So they are allowing for air to move through. That enhances microbial decomposition. They may, as they're moving through the media, concentrate, particular aspects of the fertility, whether it be nitrogen components or compounds or phosphorus compounds, into the casts, and they're allowing for transformation to occur by moving the microbiology through that media mix. I wasn't able to find an illustration of that burrowing effect in a compost media from earthworms, but this image here is the effect of burrowing of earthworms through different types of soils. So you can see they had loose soil cores versus compact soil cores, and the white dyed parts of the images are the movement, the burrows of the earthworms through these particular, an anthracene and a luisol, these silt loams, one that was compacted cores versus the loose cores. So you can see if the material is looser, the earthworms are highly mobile, and certainly they're creating a large amount of burrows and certainly enhancing the mobility of air through, as well as water and other things. So these are very active organisms, and it doesn't take very many of these earthworms to start generating casts. I think the 250 worms can generate about a liter a day of cast once the whole system is going. And so if we look at the micronutrient contents of vermicomposts, again, this is an illustration of the "you are what you eat." So these are haricot beans, grass, mixed straw, teff, maize, sorghum, different substrates that are being digested and processed by the earthworms in a vermicompost system. And there are slightly different characteristics. Total nitrogen changes a little bit between 3 up to 4.26. Available phosphorus ranges from 775 milligrams per kilo, parts per million, up to just under 1,300 parts per million in the grass. So the "you are what you eat" really does play a role. And when we look at vermicompost with respect to their role in enhancing plant yield or shoot and root biomass, we can see here that the origin of the vermicompost does play a role in the efficacy and yield. So in the top, under yield, green waste versus cattle manure, the cattle manure plays a slightly better or higher role in improving yields than the green waste. Again, similarly for shoot and similarly for root. However, other materials like paper waste and pig manure seem to have very strong positive effects on root biomass. Pig manure and paper waste and food waste seem to have a moderate improvement over a control, which is the zero. The dashed line is the control in treatment in this particular study that I drew this from. So the vermicompost do have a range of different benefits depending on the nature or the source of the raw feedstock that's being used. The insect-based proteins is becoming a a new area, novel area of exploration. It's been around. I think it's been around in human history. Humans at some point needed to obtain protein, and in some locations, insects were a viable source, and they're being evaluated scientifically again as a viable source of protein. And so, black soldier fly is one of these insects that's shown to have some potential value as a protein source in feed. And so here's a life cycle of the black soldier fly, and specifically as the soldier fly moves into that larval stage, can be fed a range of different types of organic biomass, or we would call them organic waste. But I really want us to be thinking about these materials, that these are byproducts either of consumption or byproducts of another process. View these byproducts as new resources towards new products. And so as these larval stages are being fed these materials and processing what some may consider a waste, but we want to consider a resource, they're generating a frass. And so this frass is really a mix of that waste residue, some of the shed skeleton or exoskeleton of the larvae, as well as some of the feces, some of the material that's already been digested through their system. And so the larvae become become the primary product, the animal protein source, and the insect frass is being evaluated because of its more its ease to handle. It's a material that is quite fine. It's almost like a fine powder, and so it's essentially in a form that's easily handled. And the nature, the chemistry of the frass will depend on the nature of what it's being fed, and therefore we can start to make decisions on how that frass can be used, whether it's going to be used directly as a soil amendment for fertility, or it may be used as a soil amendment for fertility in combination with other properties such as enhancing the soil microbiology, or enhancing soil microbiology as a way to reduce pathogenic organisms or the plant disease agents or vectors. So that there's continuing and growing research in this area. There are other insects that are being evaluated, and their byproducts being evaluated for use as a way to generate soil amendments. And so I wanted to present this new sort of a novel concept that that really starts to bring us closer towards a circular economy framework, which is definitely a way that we need to go. We have to stop thinking about these terminal endpoints of a waste material or waste organic waste, and thinking about those materials as really just the next stage of a larger circular process. So if we look at the nutrient chemical composition of the black soldier fly larvae frass, you can see roughly 70% dry matter, organic matter content upwards of 86%, pH a little bit over neutral. Again, a slight C-N ratio slightly above the microorganisms, and different total nitrogen, phosphorus, and potassium contents. And these are averaged values. If illustrating here in the table on the right-hand side, these values will change somewhat depending on the type of diet that the larvae are being fed. So whether it's pig manure with NPK of 2.4, 2.1, and 1, or brewery spent grain with an NPK of 3.6, 2.5, and 0.3, or household waste of 2.2, 0.5, 0.7. The nature of the feed source is going to determine the nature of the feeding substrate, and it allows us to make decisions on how we want to target and potentially use these products under different production settings. I want to talk a little bit about anaerobic digestion and digestates. This is another area of increasing interest. Potential feedstocks that can go into anaerobic digestion are quite varied. Typically animal manure such as dairy and food waste have been major sources of materials of feedstocks going into anaerobic digesters, but wastewater, sewage solids, as well as specific energy crops or other crops like silage corn have been used as well for the process of anaerobic digestion. And critically, what's generated from anaerobic digestion is a biogas that contains about 60%, a high proportion of methane. And that methane then can be combusted combusted for the generation of electricity, for renewable natural gas that can be used as a vehicle fuel. And in that process of combustion, also generates heat that can be cycled back into the process or maybe cycled into other integrated systems around the digester. The other product from anaerobic digestion, and here's where we start to move into the concept of layering the value opportunities within different processes where we're generating soil amendments. The other product is a digestate, and the digestate itself is a partially digested, organic resource that can be further converted into an organic fertilizer. It could be components of it can be converted into animal bedding. There may be other products, but certainly the fertility value in this digestate has lots of opportunities in terms of broader, larger scale, intensive crop production. So an example of the nutrient content of a digestate, here we look at food-based digestates versus manure-based digestates, pig slurry and cattle slurry. Land content will vary based on the nature of the material that's being used in the digester. It also influences the potassium and the potassium and the phosphorus components. What I do want to illustrate, though, that a critical consideration for anaerobic digestion, one of the critical considerations for anaerobic digestion is the low dry matter content. So typically, the total solids content of the feedstock or of the mixture, the slurry that goes into the reactor is less than 15%. So it means that we're working with a material that is quite high in water. And therefore the material that is coming out of the digester will also be quite high in water. Retention time of the materials in the reactor will in a wet reactor typically ranges from about 30 to 45 days, and then that reaction temperature is often in that mesophilic range, 30 to 45 degrees Celsius, which means that this particular process may not be achieving some of the pathogen management, pathogen control that you would get in a more conventional composting process. However, the anaerobic digestion value comes both in the energy production, so the capacity to use the embodied carbon from the organic materials that are being processed and converting that directly into a compound that can be combusted and used to generate electricity. And so really it's a trade-off of different value opportunities, but it does mean a different response for management of the digestate on the other side. So you're dealing with a much higher moisture material on the other side with respect to the digestate. When we look at some of the research that's been done, and there's been a lot of research done looking at digestate use for agricultural production, its use as a way to provide fertility, particularly nitrogen to soils. One study here, just for illustration purposes, showing a ryegrass test crop that had digestate added as a function of the total nitrogen as a total nitrogen treatment. So they had a digestate at 90, 180, and 360 kilos of N per hectare, resulting in an subsequent increase in total plant dry biomass from 11 tons per hectare up to 23.5 tons per hectare at the highest nitrogen treatment rate through the digestate, as well as much improved apparent nitrogen recovery in the plant. So this means that the plants, the ryegrass, the test crop, was able to take up a much larger proportion of the nitrogen that was being supplied from this digestate. So considerations for anaerobic digestion and the digestate is the process itself can allow this tiering of value through the generation of energy from the combustion of methane. However, that may be offset in the early stages through a high initial capital cost that can range in the millions of dollars for the reactor itself, the building of the reactor and that technology, as well as the supporting infrastructure and the purchase of the combustion system. So there often needs to be a subsidy component, some sort of a COMFIT or some sort of a feed-in tariff program that supports that initial capital cost for production farms or farms that may have a large amount of biomass that they see the opportunity to convert into these different layers of value, but this is not something that's entered into at a small scale. Typically, these systems require a highly liquid fraction as a slurry, often less than 15% solids, which means that you're dealing with a high liquid fraction of materials as a digestate, and that can convert into more traffic. So you're using more tankers to spread over fields, meaning that you've got more machinery that is driving over the fields more frequently. There's fuel that's expended in moving the digestate over the fields, and you need to have a substantially large cropping land base that can accept these materials on an annual basis. However, the long-term value of the digestate as a source of macronutrients, may offset that high water content. So, just to, finally with anaerobic digestions, it is a system that is generating an explosive gas, the methane. So there is some technical capacity required for the operation and regular equipment maintenance, but these are typically packaged in with the engineering companies that will be involved in providing that technology to the users. The last topic that I want to discuss today is biochar. This biochar is over the last 30 years or so, it has really presented itself as a savior to some extent of climate change. That hasn't quite materialized in a real sense. And essentially, biochar is the conversion or the thermochemical conversion of a raw feedstock. You can see the hand on your right-hand side versus the hand on the left-hand side, the conversion of that raw feedstock into a char product, charcoal product, essentially. This is done most often in using a technology or a process called pyrolysis. And pyrolysis is a thermochemical conversion in a reactor where the temperature is increased in the range of 300 up to upwards of 800 degrees Celsius with no to very, very low oxygen, and so there's a catalytic conversion that process by sort of subsequent byprocess that can occur to generate hydrogen, but that tends to be more expensive. So the basic process is the generation of these vapors that can be condensed into a syngas, but they may also be you may also extract other value products such as a bio oil and the biochar. So this is a thermochemical process that has a front end requirement of an energy source, a feed-in source of material, and has certain requirements of the raw feedstock itself, both in terms of the particle size. Typically, particle size needs to be relatively small. with high surface area, and the moisture content of these materials tend to be, the requirement tends to be very low moisture content, almost a dry material going through. So you need a finer powdered like material, or very sort of fine material like a sawdust, with a moisture content somewhere around 10 to 15%. Meaning that there's some pre-drying that may be required in order to generate these different types of char products. There are other intermediate thermochemical processes that that can generate a biochar as well. One that has a bit more flexibility, called gasification, where some small amount of pyrolysis also occurs, but there's a little bit more oxygen in those that can enter into those systems, and the physical requirement, the moisture requirements of the feedstocks is a little bit less stringent than pyrolysis. But typically biochar is considered a pyrolytic product, and generates a bio oil, a biochar, and a syngas through that process. As you can see in this figure, this set of figures here, the temperature as well as the residence time plays a fairly significant role in the proportion of the products that are generated, whether it be the biochar, the bio oil, or the syngas. So the syngas is similar to the biogas in the anaerobic digestion. It's a mixture of gases that has a larger proportion of methane that can then be combusted and used for generation of electricity and heat. The bio oil hasn't achieved a high market entry yet, but it is a material that can be used for biodiesel production, and there may be other uses for the bio oil. Typically, higher proportion generated at slightly higher temperatures of about 500 degrees, whereas biochar, the higher proportion of biochar is produced in the range of 300 to 400 degrees Celsius. Some of the physical properties that allow the biochar to provide some of the benefits that are being found are the nature of the surface areas that it opens. So it creates a large surface area of charged surface area that allows for a range of different chemicals to bind to those surfaces, both interior surfaces as well as exterior surfaces. So here are some scanning electron microscopy images of a corn cob, cassava rhizome, and cassava stems, and you can see the nature of these, kind of almost a honeycomb type illustration of the surfaces. So these interior surfaces and exterior surfaces would provide spaces for different chemicals to bind to. And so the benefits that have been found around biochar, which makes it a potentially very exciting series of products, is its capacity to moderate pH and cation exchange capacity. Though the cation exchange capacity through the charged surfaces provides a more stable carbon fraction. So this is a carbon fraction that, after undergoing thermochemical conversion, a carbon fraction that may decompose at very slow rates, and therefore may help in the sequestration and storage of carbon in soils. There's been a number of studies showing the capacity of biochar to either hold on to nitrogen ions or release nitrogen ions at slow rates, meaning that they can act as a slow release fertilizer source, or in some, depending on the feedstocks, may act as a source of nitrogen and phosphorus. A number of bacteria and fungi can reside on those reactive surfaces, and so it may act as a habitat for microbial biomass. So there's a range of physical properties around biochar that really have made it a substantially exciting new product. However, there are the considerations around the energy requirement to generate and process these materials, relative to those benefits. To illustrate what that looks like, you can see here I've taken a study out of Utah, where they were applying up to 15 tons per acre. You can see what that looks like from 1 ton up to 15 tons per acre applied to the surface, and then subsequently mixed in. outcomes of another study looking at, this was a study in Newfoundland, looking at the use of biochar mixed in with different either chemical fertilizer or a fish meal at either half rate or full rates. You can see the biochar treatments on the bottom illustration here, whether it's half rate fertilizer or half rate and full rate fish meal. Certainly much greater plant production outcomes than just the fertilizer or the fish meal alone. When we look at that with respect to actual final yields ranged somewhere just close to around 8 ton per hectare for this canola greens, up to around 13, 14 ton per hectare with the treatments that received the biochar in combination with fertilizer or fish meal, whereas the range for the control or the fertilizer and the fish meal went up from just above 0 to about 1.5 ton per hectare. So significant yield differences, particularly in combination with other fertility sources. Another illustration of that on the left-hand side, the same study in Newfoundland. This is looking at different rates of biochar and beet biomass yield. Biochar rates, tons of carbon per hectare of 10, 20, 40 tons carbon per hectare. And we've been seeing subsequent increases in beet yield. And in a study out of the US, when we're looking at the mean soil organic carbon concentration to a depth of 10 centimeters, it did vary. At 10 to 20 tons per hectare of biochar did vary based on the crop that was being grown as well as the soil type. So there isn't a universal outcome from biochar. It is very dependent on the nature of the biochar itself, based on the process that it undergoes, both temperature, retention time, and the feedstock source of the material. But it is an area that's being very highly explored for, again, the multiple layers of possible benefit that the biochar can offer. So some final thoughts for the webinar today. Biomass conversion, whether it be thermochemical, biological, provides many different opportunities to create new resources, to use these resources that we consider to be, in some cases, organic waste that need to be managed. And these materials have value for agricultural production and environmental stewardship. But there are a number of considerations on the processes that include the available land that you may have, both for the housing of these different approaches. Composting approaches may have a requirement for a certain amount of land base to be able to mix materials and house them while they decompose. Likewise, the anaerobic digestion facilities do have a relatively significant footprint. And then thinking about the purpose for using and creating the amendment, the type of capital investment requirements that these different processes may require, and then what those ongoing management costs are relative to the value or the series of values that you can get from them. And so key to recognize that generating any kind of an amendment through these processes that I've identified today, and any other processes, really are processes that generate different tiers of value. And so you need to take those tiers of value into consideration in the overall equation for whether to move in a direction of one technique or approach versus another. So as before, I'd like to acknowledge the OFCAF program and Perennia for running this series of webinars, Dalhousie University, whom I work for. And again, we don't get the plants unless we manage the soil. And so important to consider all of these factors together and how they interact and how they interact around the decisions that we make. Thank you.
Thank you very much, Gordon. That was fantastic. I really enjoyed that. I appreciate your time with this.
Thank you. And I think I'm a little bit over my 40 minutes, but I'm happy to stick around and answer any questions people may have.
Okay, well, we'll open up the floor for people here. And I can start though. And I think you did kind of answer it though, because it sounds like there is tiers of investment and goals, I guess. But when you were kind of going through digestion and especially at the end there, I was thinking about us regionally and trying to think what would suit best, if you were to, we have a lot of feedstocks around. We have manure, we have a lot of biomass from forestry, and so on. So I was kind of thinking maybe there was a conversion that would fit best, but it's probably
Well,
way too hard. We don't have a lot of land
yeah,
either.
no, and I think that's where, I mean, we're often not thinking about the like one production system is not thinking about another production system. So a forestry production system is not thinking about some of the biomass that they generate that they don't necessarily use. That doesn't necessarily add any value to the forestry system if it's left behind. I mean, I'm all for leaving a lot of organic matter behind in managed forest systems, but there may be the case where there's additional biomass that could be cycled through a process. Let's just say a composting process where you take, some residuals that don't need to be left at the forest site, and those residuals have a particular value, say for soil stabilization, for as an offset for absorbing free moving nutrients. So I'm thinking about, let's say New Brunswick has a high level of forestry and a large amount of additional forestry biomass, that if some of that proportion was composted and was able to be moved over to intensive potato production conditions in PEI, again, the distance is large, but not so large. I mean, they're neighboring provinces, relative to the need and some of the issues that the PEI is experiencing, both in terms of the high flow of nitrates into some of the rivers, which has impacts again on the fisheries, but also has impacts on local water quality for drinking water. The intensity of the production systems, for potatoes in particular, where you're moving a lot of soil, potentially creating conditions of higher erosion, may be offset by bringing in products that not necessarily are giving a fertility value, but are providing greater structural support for those soils. And that's an amendment. And so I think, looking at the global picture, what is the cost to the PI for, the loss of soil, the potential contamination of rivers or waterways, the loss of certain fisheries, or closing of certain rivers for fisheries because of fish kills, the loss of nutrients from those soils through leaching. And so, if we're looking at that global cost and the cost of composting or transporting forestry materials from New Brunswick, maybe there's a lost opportunity there that we haven't taken advantage of. Likewise in Nova Scotia, we have lots of areas where we have high fertility sources of fertility in terms of organic materials that are generated, but their water content is high, and so considering processes that maybe allow drawing down that material, or not creating a high moisture byproduct to begin with. We have dairy systems that are creating a higher water content byproduct, because it makes it easier to clean barns. Um, and maybe reevaluating that in the context of ease to transport to another location that could use those nutrients. But again, it's tough where our systems are quite separated physically, and we're not, we're at the beginning now of trying to think about how we integrate different systems to be able to make use of a byproduct in one system towards another one. I see a question. Biochar seems to be extremely popular. Rates you showed, up to 15 tons per hectare, are likely going to be more expensive than crop value for several years. So yeah, and so Dave, thanks for that question. That's I actually included those high rates in the figures on purpose, to basically identify that's one of the biggest bottlenecks currently for all the excitement and investment in biochar research. We really don't have the capacity to generate the kind of tons per hectare, um, that some of these studies are suggesting are needed to generate those kind of positive effects. So it really comes down to a grower isn't really going to look at making that kind of an investment unless they can see some real tangible short-term value or returns and value. And I guess the potential generators of biochar are likewise not going to make the type of capital investment that's required to generate that kind of tonnage unless they can sell that kind of high tonnage to growers. And so we're in a bit of a catch 22. And thermochemical conversion is highly energy intensive. So until we reach a point where it's either part of a natural process, meaning like we have an industry that generates some type of a char-like material that has maybe biochar-like qualities as a normal byproduct that is close enough to the agricultural areas. And then it's likely we're it's similar to wood ash. And if we think about wood ash, there's some mills that have been generating a wood ash that certainly was evaluated to meet certain specifications, environmental specifications, agronomic specifications, and so then they become part of the nutrient management planning for Nova Scotia. So we need something that, some industry, so it may be an industry that's generating a bio oil for a high value market, but through the generation of the bio oil are generating some quantities of biochar that then they're tiering their value in their processing to generate a biochar that they can sell to a secondary agricultural market. But I think we're still a long ways from that one. I wanted to include it because you'll often see biochar out there, and there are studies evaluating the use of biochar possibly as in smaller quantities in a mixture with compost to try to take advantage of that high surface reactivity to hold on to more of the sort of free moving ions that we want to retain in the compost. And so there's an opportunity to use a smaller amount and try to enhance the value of a compost material that can be then distributed into agricultural contexts in much larger quantities.
That's awesome. It's exciting to think about, at least in the opportunity that could be there in the future for us.
Mhm.
Um, if
And and
that,
and and again, that just sorry to we're may often be thinking about these amendments in sort of a specific context of large scale crop production, and in many instances, and amendments can be created that are being targeted to other smaller scale or maybe intensive, but in a different way. So we could be looking at greenhouse production as intensive systems that don't require the 10, 20, 30 ton per hectare amendment rates. They may require much smaller, or they may be able to get away with much smaller amendment rates.
that makes sense. I was thinking too about dehydration, and you mentioned the fish. Was it fish meal that was being used in a study in Newfoundland?
Hmm.
There,
Yep.
does fish or any kind of byproduct from our fisheries, does that go through any processes prior to application?
I think that depends on the facility generating the fish product or byproducts. So I think there, like in Nova Scotia, there's a lot of offal that's generated from fish processing. So as they're filleting fish, that offal may or may not get processed further. It may just go to an organics facility, or may even go to landfill. Certain more say terrestrial based aquaculture systems have to deal with the I guess you'd call it the settled solids from their tanks, and so those settled solids have inherent value in terms of fertility value, organic matter value, but it's finding the opportunity to either dry it down or a more local opportunity to apply that material to local cropland and then manage it. And again, it could be in a raw form, it could be processed in a compost, But again, the trade-offs that considerations that I was trying to illustrate through this particular talk, sort of highlight, one of the biggest challenges that we have, which is water content, and that's either water content introduced for anaerobic digestion to create that slurry, or it's the inherent water content of these materials to begin with, and how do we manage that water content? That's always the big challenge, but um, it's doable. It may be not doable at these very large scales that we think about for intensive systems.
That's fair. And is there anyone currently in Nova Scotia or the Maritimes that has a digester between two farms or?
Yeah, there are at least two farm-based ones that I'm familiar with. Three actually. There are three that I'm familiar with. Two are, I would say, more traditionally farm-based, and accepting different types of materials, either sort of commercial, residential type source separated organics, possibly mixed in with manures. I think there's one that is operating, again, trying to find the right mixture with different fishery waste materials, um, different processing of fishery products. The challenge with fishery products is that they tend to be very high in nitrogen, which in these anaerobic conditions are generating the nitrogen that's being generated is ammonia, and that ammonia can then often shut down the sort of the reactive conditions, other biological conditions in the soil, in the reactor for the digestion. So really, anaerobic digestion is similar to composting, where you are trying to moderate and manage that environment, to optimize the organisms that are going to thrive for that chemical process. So whether it's a aerobic process, or like an oxidation process, or sorry, my phone's going crazy, or whether it's a sort of reduction process in anaerobic digestion. So there is quite a bit of care in management of what feedstocks can go into the mixture, and at what amount. It doesn't mean that you can't have mixes. You just have to be careful with how you introduce those mixes.
Awesome. Well, we can let you go, Gordon. I
Great.
appreciate your time. Thank you so much. So we'll be here next week this time for the last one, and it'll be on biosolids.
It'll be on biosolids. The biosolids story next week.
Yes, I can't wait.
All right.
Awesome. Well, enjoy
Thank
your
you,
week.
everyone.
Thank you so much. Take care.
Have a good night.
You
Bye.
too. Bye.